Let's now talk about finding the arc length of a continuous curve from A to B. So if we were to take this curve I have drawn here, if we were to take this curve and lay out a string, tack a string onto it, cut it on the two ends, and then take that string and lay it out horizontally so that we could measure it using some sort of measuring tool, that's the length that I'm looking at. What is the length of that curve, the arc length of that curve? And so we're going to do what we've done with our other applications of the integral. We're going to break up that curve into little segments along the x-axis, and on each of those segments we're going to use an actual line segment to estimate the length of the overall curve, and then we'll just increase the number of line segments that we're calculating until we let the number of those line segments go to infinity, and it will be the length of the actual curve. So let's take a look at what that looks like with a little interactive image from the ebook. Okay, so here you go. Here you can see on this graph right here, you've got a curve, and from A to B, if we wanted to calculate the length of that curve from A to B, we could divide it up. Now notice it's only divided up into two intervals right here so that we can really illustrate this. And on each one of those, if we could calculate the hypotenuse of these right triangles that are given, we would have an estimate for the length of the total curve. Now obviously it's not going to be the exact value, but we're going to let the number of those triangles get increase, 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 so that the line segments themselves get smaller and smaller. We continue to add them all up, and we're going to end up with an integral. So how do we calculate the length of that line segment? Well, we're going to use the Pythagorean theorem. Notice that the horizontal leg of each of those triangles is delta x, and the vertical leg of each of those triangles is a delta y sub I, delta y sub 1 and delta y sub 2. Now notice that while the horizontal leg of each triangle is always going to be the same based on how we divide up the interval, and that being our delta x, that the delta y sub i's are changing based on the curve, right? Like how much change is there in the curve across that interval. So that's what we're going to do. We're going to take each of those. Again, I've brought it back to 2, but let's take it back out. So notice as we shorten delta x, make delta x smaller, which is what happens as n increases, the number of estimations we're using increases. Notice that those little line segments are getting closer and closer to giving us the actual length of the curve if we add all those up. Okay, I'm going to go through this proof pretty quickly. I'm not going to actually write this one up. I'm going to go through it pretty quickly. I already have it typed so that we can get right into an example. So let's head back over to the typed up proof here. Okay, so you can see here we were talking about finding that length. We already talked about using the Pythagorean theorem. You can see that Pythagorean theorem coming in right there. It can also be shown using the distance formula if we actually put ordered pairs on those points, but I'll talk about the Pythagorean theorem. Using a little bit of algebra, I just factored a delta x squared out of those two terms, which left me with this, and then took the square root of the delta x. It is a length, so it is positive, so pulled that outside of the square root. And then the next thing that we look at is we pull from our mean value theorem, and we take a look at another way to express this delta y sub I over delta x quantity squared. I've restated the mean value theorem right here at the top of the page, but basically what the mean value theorem says is that if we know delta y sub k over delta x is the slope of this line, which it is, through 2 points, then there has to exist a value, we'll call it x sub I or x sub k star, where the derivative is actually equal to the value of that slope. So if the derivative is equal to the value at that point, some generic point on the kth or the ith, if you want to use ith interval, if that happens to be equal to the slope, then we can do that quick little replacement in our formula that we already derived from the distance formula, the Pythagorean theorem, and find a very nice formula for the arc length of a line segment. I'm going to try to get this all on the screen at the same time if I could. And so I just rewrote the two formulas here at the top of the page. So we take our two formulas that we've already talked about, the right one from mean value theorem and the first one from Pythagorean theorem, make a substitution and do a little bit of simplification. There we go, make the substitution, do the simplification, and then actually I move the delta x to the end of the square root. That is the length of every single line segment. But again, remember, we're going to add up all of those line segments, and take the limit as we go to infinity. And what that does is it gives us an integral. So our arc length formula is an integral from a to b of the square root of 1 plus the derivative of f of x squared dx. And so let's go ahead and go over and summarize all of these in a single formula. All right, so now on the screen you can see, now that we've briefly talked about how these formulas were derived, you can see the arc length formulas. The first one is if we have a function y equals a function of x on an interval from a to b on the x-axis. As long as that function has a continuous first derivative, then the arc length is going to be equal to the integral of the square root of 1 plus the derivative of that function squared with respect to x, so dx. I wrote this both in prime notation as well as Newton's notation as well as Leibniz notation with the differential dy dx. So you can see both of those notations here. And of course, just like with our volume formulas, just like with our area formulas, if instead of a function of x, if we're given a function of y and it has a continuous first derivative and it's along the y-axis from c to d, so you can see here we're along the y-axis from c to d, then we can find the arc length of that function by taking the integral from c to d of the square root of 1 plus g prime of y squared, and this time it's going to be with respect to y, so dy. So we can definitely use that formula, and of course when we use the Leibniz notation, the differential notation, it will be the derivative of x with respect to y, so dx dy, quantity squared dy. So if you haven't already put these notes in your formula, or these formulas in your notes, please do so now, because these are formulas that you will need to know and have memorized in order to calculate arc lengths. Now we're going to go ahead and take a look at an example. All right, so if we wanted to find the arc length of this curve, it's an exponential function or a combination of exponential functions. Y is 1/2 e to the x plus e to the negative x on the interval from negative natural log of 2 to natural log of 2. Well, we're going to need our arc length formula. And so we know that this is going to be equal to the integral from a to b of the square root of 1 plus f prime of x quantity squared dx, or a to b, if we want to think in terms of Leibniz notation, dy dx, the derivative of y with respect to x, squared dx. So we need to plug into that formula and simplify and calculate. Now, this whole square root of 1 plus a derivative squared can be simplified often a lot before we jump into the integral. So I'm going to take all of that off to the side. I'm going to take my function. My function is y equals 1/2 e to the x plus e to the negative x, and I'm going to find the derivative. I'm going to go ahead and use dy dx since this was written as y instead of f of x. So the derivative of y with respect to x, so we're just taking the derivative of an exponential function. It's 1/2 e to the x, because the derivative of e to the x is e to the x, and then the derivative of e to the negative x is negative e to the negative x, because we had e to the negative x times negative 1. All right, so that's the derivative, and now I need to take that derivative, I need to square it, add 1, and take the square root. So this is what I mean by, before I plop it into the integral and think about how to integrate this function, I want to see if I can get this square root as simplified as I possibly could. So let's see. So what's that going to look like? That's going to be 1 plus 1/2 e to the x minus e to the negative x quantity squared. So then that's going to be equal to 1 plus, that's 1/4. And then let's go ahead and expand out that e to the x minus e to the negative x squared. So let's expand that out. When I do that, I'm going to get e to the 2x. I need a little bit more space. So I'm literally, just little thought bubble on this part. I'm taking e to the x minus e to the negative x, and I'm squaring it. So that's an e to the x minus e to the negative x times e to the, times e to the x minus e to the negative x, and just expanding that all the way out. So that's what I'm doing, just so you know what I'm thinking through in my head. So I get an e to the 2x, and then the middle term ends up being a minus 2 times e to the 0. So where does that come from? That question often comes up. So right when I expand this all the way out, I should have made my thought bubble a little bit bigger. Let's erase that so I can make my thought bubble a little bigger. When I expand that out, I get e to the x times e to the x. There's the e to the 2x, and then I get I get e to the x times e to the negative x. Now right there, that's where we get negative e to the 0, because when you multiply two of the same base, you add their exponents. But then you get another one of those as well. So you get negative x e to the negative x, and then you get a positive e to the negative 2x when you're expanding this out. So notice that those two middle terms there become minus 2e to the 0, but minus 2e to the 0 is just minus 2. So that was a little bit of review on algebra. I was realizing I might be going through that too quickly in my example here. So I'll take that off to the side so we can see that. So we get e to the 2x minus 2e to the 0, which of course will just become minus 2, plus e to the negative 2x. Okay? I'm just using some algebra. There is quite a bit of algebra in this particular problem as we're simplifying this square root. So let's keep going, see what else happens here. Because that, of course, is just a minus 2. So this, let's go ahead and write that in. E to the 2x minus 2 plus e to the negative 2x. And then keep going. Let's distribute. So we get 1 plus 1/4 e to the 2x minus 1/2 when I distribute the 1/4 plus 1/4 e to the negative 2x. And then we got a 1 and a minus 1/2. And so I'm going to add those together. And it might seem kind of funny, but I'm going to leave it in between the two exponential terms because as crazy as this might sound, that is actually a perfect square. So this is a perfect square. And we have a similar perfect square right above. It was the one we just expanded. We didn't have the 1/4 in there, so if we wanted to, we could factor that 1/4 out. And let's see what that looks like, and then we'll actually be able to see it exactly like compared to the one we did before. So if I actually factor a 1/4 out of each of those terms, because we want to be able to see what happens, this becomes e to the 2x plus 2 plus e to the negative 2x. And look at this. Draw your eye to the expansion we had right here and to what we have right here. These are two perfect squares. And that's so that e to the 2x plus 2 plus e to the negative 2x, that actually factors simply into e to the x, not 2x, e to the x plus e to the negative x quantity squared. Okay. And we see the expansion up above right here. I'll highlight it where we did that little thought bubble when we expanded e to the x minus e to the negative x squared. We expanded that out. And you can see we ended up getting that e to the 2x minus 2 plus e to the negative 2x. Well, here, instead of a plus 2 in the middle, or instead of a minus 2 in the middle, we had the plus 2 in the middle. So the only difference was the expansion of the binomial had a plus there between the two exponential problems, or between the two exponential functions instead. And that is very convenient. Oops, I copied down the 1/4 wrong. That should be the square root of 1/4, not the square root of 1/2. When I was writing, I was rushing into the exponentials and I copied that down wrong. So check that out. We now have a square root that has a perfect square underneath it. The square root of 1/4 is 1/2. And of course, the square root of e to the x plus e to the negative x squared would be the absolute value of e to the x plus e to the negative x. Right? When we take the square root of a square, we actually do get that absolute value. But when we add two exponential functions, they're always positive. So this is just 1/2 e to the x plus e to the negative x. And that was very, very convenient that square root of 1 plus the derivative of our function squared actually worked out that way. There's a lot of algebra in there, so pause the video and look at those expansions and then the refactoring of that perfect square if you need to. But that is what we're going to be integrating to find the arc length. So now we're going to take that and we're going to put it into our arc length formula. So the arc length, I'll keep it on the screen for just a second, then I got to zoom in. So our arc length is going to be the integral from, now remember we wanted to go from negative natural log of 2 to positive natural log of 2, and it's the square root, I'll write this, 1 plus dy dx quantity squared dx. But remember, we just calculated that. We did all that work off to the side. So that's just going to get replaced with 1/2 e to the x plus e to the negative x dx. And that integral, since I've already done all the work, right, to simplify, so that was all my side work, since I already did all that side work, and it was some pretty intense algebra side work, but we already did it all, and so now all we have to do is integrate. And this actually works out to be a very nice little integral because we can pull the 1/2 out in front, and then we're just integrating an e to the x, which is e to the x, and then we're integrating e to the negative x, which is, it ends up being e to the negative x over -1, because this is a -1 right here. But I'm going to just write that as negative e to the negative x. And we're evaluating it from negative natural log of 2 to positive natural log of 2. And so we plug those values in, and we get 1/2 times, I'm going to pull the 1/2 all the way out in the front, 1/2 times e to the natural log of 2 minus e to the negative natural log of 2 minus e to the negative natural log of 2 minus e to the positive natural, because it's negative natural log of 2. All right, and we've got some signs and some things to simplify here. So again, the actual calculus there, the integration, was pretty easy in the plugging in, but we've had quite a bit of algebra on this problem. So I just want to finish, before I actually apply rules of exponentials and logs, I'm just going to finish writing this. This is e to the natural log of 2 minus e to the negative natural log of 2 minus e to the negative natural log of 2 plus e to the natural log of 2. So we got 2 of each of those. So we end up with 2e to the natural log of 2 minus 2e to the negative natural log of 2. But we also have a 1/2, so then we distribute the 1/2, and we get e to the natural log of 2 minus e to the negative natural log of 2. Now I'll apply my rules of exponentials and logs. When we have e to the natural log of 2, that's just 2. And right here, this negative can come in as a power. So this can become minus e to the natural log of 2 to the negative first. And so again, when we take the exponential of a logarithm, e to the natural log of 2 to the negative first, we get just negative 2 to the negative first. But 2 to the negative first is 1/2. So this is just 2 minus 1/2. And my answer is 3/2 units of arc length. Remember what we're calculating here. We've gotten into some, it's funny, this particular problem had just boatloads of algebra. We did a lot of algebra as we were simplifying, but to remember what we're doing here, we're finding arc length. And so there, I'll get it all on the screen at one time. I want to mention on this particular problem, I did the same problem. This is the first problem on the worksheet. And so I'm doing the first problem on your worksheet, but there's another way to do it. And I want to encourage you to think about the hyperbolic functions. Hopefully your Calc 1 teacher talked about the hyperbolic functions and kind of their basics. And what I want to do is I want to zoom in on this original function right here. And you could have actually avoided most of this algebra if you had noticed that this right here is 1. So when we have 1/2 e to the x plus e to the negative x, that is exactly how the hyperbolic cosine of x is defined. And so you can do this problem. You can do the whole problem with hyperbolic functions. And that is a very nice way to do it. It actually saves us some work on all the algebra that I showed here. We don't have to if you don't remember the hyperbolics, that's okay. Those are coming up next week. We're going to review hyperbolics. But if you would remember the hyperbolics, and it's one of those things I always tell my students, the hyperbolic functions, we talk about them and we utilize them. We don't always have to use them. We can always go to their exponential forms, or in exponential form if we don't recognize that it's a hyperbolic. We can just use what we know about exponentials, but they can often be really handy. So in this particular case, you can take a look at the solution when I post it for the worksheet. In this particular case, the hyperbolic way to do this problem, or using hyperbolics to do this problem rather than leaving them in their exponential forms, I believe is a cleaner way to calculate this arc length. Do you have to do it that way? No. I just showed you how to do it just using the exponential form. But if you had happened to catch that that was the hyperbolic cosine, and as I was doing this problem, if you were thinking, man, I wish you would just use hyperbolics, then remember that you can do it that way too. And you can see that solution on the worksheet. All right, we'll be back for more arc length examples.